Hello friends, welcome back to All About Structural Analysis and Design. So in my previous analysis videos, you have seen how to calculate the moment, then safe load and the section, whether it is over reinforced or under reinforced, we have learned. And today's video is little bit different compared to our previous analysis videos. Okay, so I have written here problem and I will read this problem and I will show you what is the difference between our four previous type analysis problems and in this particular RC problem. Okay, so the problem given is a rectangular beam, RC beam of width 300 mm, okay, and effective depth 500 mm is given, and they have said is reinforced with 4 bars of 20 mm diameter, and it says it has a effective span of 6 meters, and the live load it can carry is 8 kilonewton per meter. So the difference in this problem is all the previous problems were very straightforward. Here what they have mentioned, determine position of neutral axis they have mentioned. Okay, in my previous videos I have not shown exactly how to find the position of neutral axis. Then moment as usual, and one more extra thing I have added in this problem is we should find how much concentrated load. Okay, concentrated load is nothing but your point load it can carry at midspan. So there are two different things compared to my previous videos. One is we have to find out the position of neutral axis, moment we have seen in our previous videos, and the next important thing which is unknown, which is different, is that what we have to find out what concentrated load, that is point load, it can carry at midspan of the beam. So that's why this effective span already they have given. Okay, so we'll start the solution, and as usual practice in my RCC problems, first we write down our given data, what all the parameters are given to solve the problem. Okay, so this is the given data. First they have given width of beam, that is 300 mm, then effective depth they have mentioned, that is 500 mm, then they have given the quantity of steel, that is 4 bars of 20 mm phi is also known as diameter. Then this effective span, small l we are denoting, it is 6 meters. Then WL, which is nothing but live load, it is 8 kilonewton per meter, and there are 3 unknowns in this problem. First is you have to locate the neutral axis, then you have to find out the moment of resistance, and then you have to find out the concentrated load or point load, which we have denoted as P. Okay, so let's begin with the problem. So first part in this problem is to find position of neutral axis. So this we are going to find first, and you have to have your IS 456 2000 RCC code book. Without that you cannot proceed this problem. So from page number 96, IS 456 2000, there is one formula. Okay, sections without compression reinforcement, there is one formula on page number 96. The first formula you have to use, that is A formula, which is XU by D. So XU by D is equals to it says 0.87 Fy AST divided by 0.36 FCK BD. So in my previous analysis problems, again we were finding out XU by D value, and then we were comparing with XU max by D value, and then we had commented whether the section is over reinforced or under reinforced. But now in this problem specifically they have asked to find out the position of neutral axis. So that's why what we'll do, this D and this D will get cancelled. Okay, so we'll cancel this from both sides. So only remains is XU. So XU is equals to 0.87 Fy AST divided by 0.36 FCK B. Now all the things are available with us, but before that we have to calculate what is AST. So in terms of bars and the diameter of bars they have given. So first we shall find out what is AST. So for that AST is equals to, simple formula, 4 bars are there, so 4 into pi by 4, the diameter of the bar is 20 mm, so 20 square. So the AST comes out to be 1256.64 mm square. So unit you have to remember all the time. So this is the AST. So this AST now can be substituted here. So we'll substitute here. So 0.87 Fy, the grade is given 415. Okay, so I think we have missed to write down the FCK and Fy value. So I will write here. So given again, FCK is equals to 20 Newton per mm square and Fy is equals to 415 Newton per mm square. So actually I have missed to write the materials in the question itself. So here I will write down, use M20 and Fe 415 materials. Okay, so you can write down here FCK and Fy. So Fy value is given 415 grade, so you can write down here, and this EST you can substitute 1256.64 divided by 0.36 into FCK is 20, that is M20 grade, and B is given here 300 mm. So after working out this, you will be getting XU is equals to 210.05 mm. So in our previous analysis problem, we had not calculated directly XU value. So this is the position of neutral axis for the given problem. So like this way, you can find out the position of neutral axis. Now the next step comes is we have to check whether the section is over reinforced or under reinforced section. For that, we have to have the value of XU max by D, and it is there on page number 70 of IS 456-2000. Okay, so now from page number 70, that is same again, IS 456. So you get there for Fe 415, there are three types of steels again. First is 250, 415, and next is 500. So we are using 415 grade. Therefore, that particular grade you have to see, and you have to see the XU max by D value. So XU max by D is equals to 0.48. This is valid only for Fe 415. Now what you can do, this D you can transfer this side and you can find out XU max value. Therefore, XU max equals to 0.48 D, and D we already know. So the D given is, the effective depth is 500 mm. Then XU max you get 240 mm. Okay, so this is your XU max. Okay, now from this, comparing these two values XU and XU max, you can comment the section whether it is under reinforced or over reinforced section. Now XU is less than XU max, so therefore the section is under reinforced. Therefore XU is less than XU max, therefore section is under reinforced section. Under reinforced section. So this is the first part of your problem where they have told to locate the neutral axis position. Now we have seen the section A is under reinforced, and based on under reinforced and over reinforced or balanced section, we have to use the correct moment equation. And again from page number 96, you will be getting that moment equation, and clearly they have mentioned for under reinforced section, the B formula you have to use from page number 96. It is exactly below XU by D formula. So the B formula we have to use. Therefore, moment of resistance okay. So again page number 96 IS 456-2000. So this is the again reference. Okay, so the formula is mu is equals to 0.87 Fy AST D Okay, 1 minus ASTFY divided by BDFCK. So this formula you can find out on page number 96 of IS 456-2000, exactly below the XU by D formula which we have used to locate the position of neutral axis. Now the procedure is again simple. All the things are known. Fy is known, AST is known, D is known, B, D, FCK. All things are known. So you have to find out directly the second unknown, which is moment of resistance. Okay. So just substitute. So mu is equals to 0.87, Fy is 415 grade of steel, AST we had calculated, it is 1256.64. So into D is nothing but your 500 mm depth, 1 minus AST 1256.64, Fy is 415 divided by B is 300 mm, D is 500 and FCK is 20 grade of concrete. So now once you simplify this, you will be getting the moment value as 187.42 kilonewton meter. So this is the moment of resistance for this particular beam section. So this is how you will be calculating your moment of resistance by taking the B formula. Why we have taken B formula? Because it was under reinforced section. Okay, I hope this moment calculation is clear. Now in the first step we have done with the position of neutral axis. Then second step we have calculated the ultimate moment of resistance. Now the third and important thing is we have to calculate the concentrated load which the beam can carry at midspan. So we have to calculate now point load. Okay, for that we require now working moment. The moment which we have calculated for the second step, that was ultimate moment. Now we will calculate working moment. Okay, so we will denote it as M. Okay, the previous mu was ultimate moment. Now it is working moment and it is calculated as mu divided by partial safety factor. Partial safety factor. So when we divide it with partial safety factor, so we will be getting the working moment, and the moment working moment is mu we had got 187.42 divided by, okay, so partial safety factors can be of various types, but for residential building and for simple structural elements we take it as 1.5. so we will be taking here 1.5, and the working moment comes out to be 124.94 kilonewton meter. So this is our working moment, and based on this working moment we will be calculating the point load. Okay, so after this we need to calculate the self weight of the beam, which is also known as dead weight of the beam. Okay, so now self weight of beam. Okay, so we will denote it as WD. D stands for dead load, and here we had taken WL, which is live load. Okay, so we will designate this as WD. How we will calculate our self weight? It is nothing but complete width plus complete depth, and we are multiplying it with density of concrete, which will be taken as 25 kilonewton per meter cube. So the formula is B into overall D into density of concrete. But before moving to this calculation, we require this overall depth, because in the problem it is mentioned effective depth. So we need to assume suitable effective cover and then find out the overall depth, and then we can proceed with the calculation of self weight of the beam. So minimum effective cover we will provide for this beam, that is 25 mm, and then we will start with the calculation of self weight of the beam. So assume effective cover D dash equals to 25 mm. So which is minimum for the beam. Okay, so 25 mm we will assume. Now we can calculate the overall depth, which is nothing but d is equals to d plus d dash. Okay, so now d is equals to overall depth is 500 mm plus this 25 mm. So therefore d is equals to 525 mm. So this is our overall depth. Now this d can be substituted here and you can get the dead weight of the beam. One thing you have to remember is this density will be in kilonewton per meter cube. So we will substitute this small b and overall depth in meters, so that we will get the dead weight of beam in kilonewton and meter. So substitute here. So WD is equals to b is 0.3 meters, which is nothing but 300 mm, into this 0.525, that is overall depth, and the density of concrete, which is taken as 25 kilonewton per meter cube. So WD works out to be 3.9375 kilonewton per meter. So this is your dead load on the beam or the self weight of the beam. Okay, I hope it is clear. Now what is the next step is we have to add this dead load and live load to get the overall load coming onto that particular beam, which is UDL. Okay, now W is equals to WD plus WL. So W is equals to WD, just we have calculated now, 3.9375 plus live load is given as 8 kilonewton per meter. So when you add it, so total load will become 11.9375 kilonewton per meter. So this will be your overall load which is coming onto the beam, which is UDL. Now once we have got the complete UDL, okay, then we can move on to our point load calculation. For that, okay, so we have to take again the working moment which we have calculated, and it work out to be 124.94 kilonewton meter. So now the bending moment formula, okay, if you remember your strength of material concept, the bending moment formula for simply supported beam carrying UDL was WL square by 8, and simply supported beam carrying point load at midspan, it was WL by 4. So same concept we have to use here, and you have to find the point load. Okay, so now this moment is equals to WL square by 8, which is exclusively for UDL, plus PL by 4. Okay, so small l I will use because that is designated as effective span. Okay, so this particular formula you have to use. Why I have added? Because this, at least it is uniformly distributed load for simply supported beam. This extra they have given to find out this concentrated load it can carry at midspan. So that's why it is the addition for that one. And from this equation you are going to find out this P, which is nothing but point load. Okay, now just substitute here working moment, that is 124.94. Okay, is equals to this W we have calculated just now, that is 11.9375. Okay, and this L effective span, that is 6 meters divided by 8, plus P will remain as it is, L is 6 divided by 4. Okay, this we will again simplify. So this works out to be 53.718 plus 1.5 P. Okay, now from this you can find out the unknown P value. Therefore, P is equals to 124.94 minus 53.718 divided by 1.5. So this is the simplification, and after you simplify or after you calculate this, you will be getting this unknown concentrated load as 47.48 kilonewton. So this is the procedure to calculate the point load it can carry at midspan, and it is 47.48. So in this whole problem, we have seen three types of calculations. First was position of neutral axis, then again your usual moment of resistance value, and then we have calculated this point load at midspan. I hope all the explanation was clear to you. Okay, and again my all four types of analysis problems, the link will be shared in the description box below. Okay, you can just check out those videos and you can be perfect in those type of videos as well. So if you have understood this video, please like it, share it, and don't forget to subscribe all about structural analysis and design, and also press the bell icon for the latest notifications of my videos in civil and structural engineering. Thank you, friends.